All right, so let's continue with a little bit more just about the kind of idea for this, for these different thermochronometer systems, and to talk a little bit about some of the things that can affect this closure temperature. So again, just as an idea, we're looking here at the approximation of the area in the middle of this kind of gray zone where you're partially retaining your daughter isotope, to say, like, let's just pick a temperature here in the middle and call that the temperature at which we start to retain, or the temperature below which we start to retain the daughter isotope. So that's fine, but there are things that affect this effective closure temperature. One of them is the cooling rate. And yeah. So, for this cooling rate, the idea here basically is that as the mineral that you're looking at cools more and more quickly, there's less time for the daughter isotope to diffuse out of the crystal. So if you go from being at a very low temperature or very high temperature and cool very rapidly to the surface, essentially you trap more of the daughter isotope than if you cool from the same temperature to the surface much more slowly. And that's in essence because there's less time for the isotope to be able to diffuse out of the crystal, and so more of it's trapped, which means that the behavior is like it has a higher temperature at which it's retaining the daughter isotope. So for instance, with apatite, if we're looking at the accumulation of helium in the crystal, you can see at a slow cooling rate, so 0.1 degrees C per million years, you'd have a closure temperature of around 40 degrees C, so quite low temperature. And if you look at the same system at a much faster cooling rate of 100 degrees C per million years, the closure temperature is about double. So it's up to 80 degrees C approximately for that system. And if you look at a different, like if you look at the accumulation of argon in the hornblende, you see the same general idea, but just at higher temperatures. So this is a system that is just retaining the daughter isotope at higher temperatures compared to the accumulation of helium in apatite. So temperature and the kind of rate at which you're cooling will be one of the things that has a big effect. Now here, this is the basic age equation that can be applied for geochronology for any kind of system where you have a radiogenic parent isotope that's producing a radioactive parent isotope producing a radiogenic daughter product. And this is basically the generic age equation, which just says that the age is going to be equal to 1 over the radioactive decay constant times the natural log of 1 plus the amount of daughter isotope, or concentration of daughter isotope, over the concentration of the parent. So that's fine. This would work for something like uranium lead and should give us a reasonable estimate. But of course, we're losing some of this daughter isotope to diffusion with the thermochronometer, so we can't use this exact same relationship with thermochronology. So instead, we have to take a little bit different approach, and this kind of goes in the direction of what we're going to do with today's exercise. I think I won't go through this in a great amount of detail just to save a bit of time, but the slides are here, or will be here on the course page that you can look at. But I'll go over the basic idea just to make sure everybody's in the same same basic mindset. So you imagine, for instance, here on the left side, you've got this set of blue and red. These are meant to represent atoms in a crystal lattice. Okay, I don't know what crystal this is supposed to be, but whatever. They're just in a regular spacing crystal lattice. You've got normal atoms that make up the crystal, so this could be, whatever, silica, oxygen, various things that would make your rock-forming mineral up. And then you've got the occasional parent isotope substituted in there. So things that aren't really supposed to be part of the crystal lattice in perfect conditions, but because they were around when the crystal was growing, they got incorporated into the crystal lattice. So this could be uranium or thorium or whatever. And these are radioactive, so they decay occasionally. And when they decay, they're producing some kind of daughter isotope. In this case, this would be like a helium nucleus from alpha decay that's then floating around trapped inside this crystal not in the crystal structure itself, but just trapped within the space between the atoms of the crystal. And these are kind of foreign isotopes, and they tend to then just diffuse out as a result over time. As we're dealing with the diffusion equation, you could imagine that we can model this to say that the change in the concentration of the daughter isotope over time is going to be equal to some kind of diffusion constant. In this case, it's a temperature-dependent diffusion constant. So it will change as a function of temperature. And then this is times the second derivative of the daughter isotope. This is basically the change in flux over some distance dx squared. And then plus P, which is the sort of parent production rate. So this is the production of new isotopes of the daughter product. So that's our age equation in this case, because we have to worry about this diffusive loss of the daughter isotope compared to the other generic age equation that we had before. The temperature-dependent diffusion part can be modeled here basically as an exponential function. So you have whatever your temperature-dependent diffusion divided by some length scale. So this is the diffusion domain. Typically, it's the size of the crystal that you're dealing with, squared, and that's equal to then the diffusivity at infinite temperature. So this is a diffusion constant times the exponential, so e to the minus, this is activation energy divided by the gas constant times temperature in kelvins. And this will basically work such that the diffusivity will decay as you go to lower temperatures. And yeah, activation energy is basically just the minimum energy that we need to get diffusion to occur. So that's a kind of constant. And then otherwise we should have this kind of exponential temperature behavior, which looks more or less like this. So as temperature, this is temperature versus time. So if you go from high temperature cooling down toward with time, what you'll see is that a high temperature, this is the daughter versus parent ratio. So the amount of daughter product divided by the amount of parent isotope in concentration. It's basically 0 at high temperature, starts to increase as the temperature cools, and at this time here, for instance, Tc, that would be the time that corresponds to the closure temperature where you're starting to accumulate the daughter isotope, and then that daughter to parent should increase with time once you're at cold temperatures because you're now in the kind of cold and closed system behavior. Don't need to worry about that in too much detail here, but basically what was done by Dodson in 1973 in the kind of classic paper was to take this diffusion relationship and make an approximation there that effectively says, okay, well, the reality is that you have this kind of curve that shows you're gradually increasing the amount of the daughter versus parent ratio, and if we just approximate that as a straight line down to some point here, that can give us our closure temperature. And in essence, this is how this this diffusion equation is working. So yeah, in essence, we basically have some diffusion as a function of time that is, again, some diffusivity at infinite, I guess it's infinite temperature here, this D naught. But this is the diffusion, I think, at the, I don't think that's the same infinite temperature, but it doesn't really matter so much for our purposes here. But then we just have our exponential being then time divided by some term tau, which we'll see in just a second, which is another way to measure how long it takes for the diffusivity to decrease by a factor of 1 over e. So e is the natural logarithm, and 1 over e would basically would be a measure of the time needed for that decrease to occur. There's some algebra in the paper. You can go and look at it if you really want to. But in essence, you come up with this term tau that relates to, this is the universal gas constant times temperature squared divided by the activation energy times the cooling rate. And this is negative by convention, so that was basically how we can get a value for this tau that's in the equation here. And the closure temperature is also done by just doing some bit of algebra to come up with something that has the activation energy for whatever the crystal is, and the parent and daughter isotope. Gas constant, natural log here. Then A is this geometry factor. So this depends on what kind of mineral you're dealing with, whether you treat it like a sphere or a cylinder or a plane. Like as you might imagine, this is suitable for micas. Tau is what we just would have calculated up here. And then D naught is that diffusion constant at infinite temperature. And then this is the size of the crystal. The issue here is that when you deal with this, we want to calculate a value for tau, and typically what you put in here for temperature is your estimate of what the closure temperature is. So we have tau that depends on closure temperature to be able to calculate it. Then we have an equation here for closure temperature that depends on tau. This is seemingly a bit of a problem, but there are ways to deal with this, and one of them is that we can iterate and try to find a solution that way by putting in a guess for what the closure temperature might be, calculating tau, putting in that new version of tau to get a new closure temperature, and just going through that process until the estimate of the closure temperature stops changing. So the basic idea here is kind of laid out like this. I think I actually put this also into our the little demonstration notebook for today. But we'll define whatever constants, make some guess for what the closure temperature is, and then have a loop where we go through, calculate tau, calculate a new closure temperature, and then do the same thing over and over again and check to see at what point does the closure temperature stop changing. And at that point, we then can say we found what a suitable estimate for the closure temperature would be. That's going to be easiest to see, I think, in the exercise itself. But with this approach, you can basically do things like, say, calculate as a function of the cooling rate what is the expected closure temperature for one of the thermochronometers, such as helium in apatite. And you can see, for instance, here that the effective cooling rate is pretty significant on the closure temperature. If I'm not mistaken, yeah, we can skip that one. That's more or less what I think we need to cover in terms of the kind of general background stuff. Again, the slides will be on the course page, so you can have a look at those if you're confused about things. But we should have a look at the few Python things we need for this week, and also a quick look at the exercise before we run out of time. So are there any questions about this closure temperature idea? I mean, I guess does the concept of the closure temperature make sense by itself? Maybe not calculating it here, but yeah.
How significant or how wide are the ranges usually for the partial retention zones? It seems like those can be like a real headache for dating things.
Yeah, I mean, they can be significant. It can span, in some cases, it could be 60 to 80 degrees C, even more in some cases. It's really, I mean, it's most difficult when you have things that are cooled slowly. So that's the place where typically you have the most time spent within that partial retention zone. So it's just the most uncertain in terms of the age that you get out of there. And usually a kind of reasonable approach to that would be to try to figure out, are there some other geological constraints that we can use to also try to reduce a little bit the possible cooling histories. That could be done by using multiple thermochronometers from the same rock sample. So you kind of give yourself a few different temperature points, but that's difficult. I didn't put it into the exercise or to the lesson today. Maybe I'll put it into one of the upcoming ones, but there's also other things that occur, like there is, for this helium system in apatite and zircon, there's an effective radiation damage to the crystals as well. So the decay process damages the crystal locally around the parent isotopes, and that can change the diffusion rate. And it can do it in a weird way. So in some cases, it can increase how much helium is retained, but then over prolonged periods of time, it can actually result in crystals that effectively can't retain any helium because they're so damaged that they're like a metamict material, and the helium is just effectively lost, even at close to surface temperatures. So things get, well, I guess the devil's in the details, but it gets nastier as you go to more, well, slowly cooled systems especially. And I mean, it can be really interesting to work with, but more challenging to interpret the data. I think the simplest cases are like these very rapidly cooled rocks in young origins, like in the Himalayas and the sort of southern Alps of New Zealand, Taiwan, parts of the Andes where the rocks are cooling really quickly. It's most straightforward to interpret the age data there. Although in some cases the rocks are cooling so quickly in certain parts of the Himalaya that you have almost very little time to accumulate any daughter isotope. So then you can run into the problem that like you've got a very simple cooling history, but you have very little daughter product to measure. Especially there are some notorious low uranium apatites in the Himalayas where you just like the parent isotope concentration is so low that you don't have hardly any daughter isotope. Then you have the opposite problem. It's still difficult to interpret your data even though it's cooled much more quickly. So, but yeah, other questions? I mean, I hope at least the general idea of this closure temperature concept makes sense. That we want to find a point or find a temperature that our age would correspond to, because essentially that's the time when the clock starts ticking in terms of what you're measuring in the accumulation of the daughter isotope. And if nothing else, that's probably okay for this week's exercise, just to kind of understand the idea that at some temperature you cool below that, and that's when you start accumulating the daughter isotope. But yeah, let's go here for a moment. I'm in Jupyter Lab on the CSC notebooks. We'll take a look at a couple things. Probably don't have time to go through everything in detail here, but we'll at least show you a couple things that are going to be useful for this week's exercise. But first I'm going to go into the My Work folder and into the notebooks subdirectory in there. And then if I go to the Git plugin, you should hopefully see if you go there that the little orange circle shows up that indicates that there's changes you can pull down. So if you click this button to pull the changes from GitHub, you should get the most recent notebook for lesson number 3. Should show up in here in notebooks. Is there anybody who wasn't able to get that who was wanting to? Yeah, so what, do you get an error message or?
Yeah, it's that
Okay. Did you by chance try to commit any changes to the notebooks before in the lesson notebooks? Because most, like 90% of the time, that's what the problem is that you've committed a change locally, and then the problem is that if you've made a commit on the CSC notebooks and GitHub has different things, it doesn't necessarily know how to put those together. Maybe the simplest thing for right now is just to kind of follow along, and then we can fix things after class. Because it won't take long, but it takes a minute. It's not a simple fix, unfortunately. But yeah, if you've pulled the changes, you should see the L3 folder here. There's only one notebook in there, I think, called Python Concepts, which is basically just the concepts that we need for this week's exercise. And there's effectively 2, maybe 3 things here that we want to look at. And I think we can start with the first one, which is about the idea of a while loop. So we've seen the for loops before, and with a for loop, typically what you're doing is you're iterating over some set of commands or some bit of code in your Python program a fixed number of times. So you might have a for loop that goes through and for every one of the items in some list does something, or loops over using the range function 100 times and does something. A while loop is sort of similar in terms of the concept, but the difference here is that the while loop will keep iterating as long as some condition is true. So what that means is that if we maybe just demonstrate this with a simple example, we could start by making some list of names. And so we could put in here me, we could put in our course assistant Levi. I think last time I did this, I put in Uncle Ismo from exercise number 1. And then I think I had put in some Woofy the dog or something like that. And let's add another one. I don't know. Yeah, maybe we'll just leave it like that with those 4. So we have a list of these different names. And one thing you might do here is you could have some example of a while loop where we go through, and as long as the name is not some name we specify in this list, we keep printing out the names to the screen. So if we say, let's start by saying I equals 0 because we're going to use the index value or the value that's associated with I to refer to the different values in the list. And we could basically have a while statement here that says while names of I does not equal, so exclamation mark equals, does not equal Woofy. Do some stuff. So as long as this condition is true, which is that the name at whatever value of I we're at does not equal Woofy, so if we get our list of things here, as long as that's true, we'll just print out names of I. And there's one other thing we have to do here, which is to say I equals I plus 1. And the reason for that is because inside of our while loop, we need to somehow increase the value of I to go from one item in the list to the next one. We could do this with a for loop as well, but it's worthwhile to see this while loop example. So when you run this, what you'll see is that first time through here, names of I, so I is equal to 0, that's going to find my name. My name does not equal Woofy, and therefore that condition is true, so then it does this code that's underneath here, which is it prints my name out, there it is, and then it increases the value of I by 1. Then it goes back up here to the loop again. Now we have I equals 1, so we get Levi, and we see that Levi is not equal to Woofy. That's true, prints the name out to the screen, increases I by 1. Same thing happens for Uncle Ismo. But finally, in the last case, we come here, we find names does not equal Woofy is false, and that's why Woofy is not printed out to the screen, because at that point the while loop gets broken and nothing inside there will be done after that. So it's a bit of a different thing. I mean, the concept of looping is the same kind of idea that you have the code indented underneath here that you want to run inside the loop. But the difference is you're going to iterate until a certain condition is met. And we could see an example of this if we do something like, there's a nice simple algorithm for trying to find the square root of some number here. And so the idea is that if we take a guess of the number, which we could call xn, we can take our calculation of what the square root would be as equal to 1/2 of the guess plus the number itself divided by the guess. And over a few iterations, this will quickly converge to give us our number that we're looking for. So imagine we have some number here. We could make it something big like that. It doesn't matter what you type in here. Just put in some big number. And we could say our guess for what the square root is, I don't know, something like this. I'm just typing random things because it really doesn't matter. But we could do this with a for loop, or we can do it with a while loop. I think maybe just for the sake of demonstrating things, I'll just show you with the while to save some time. But let's say that one other thing we can define is our guess difference. And this is basically how much our previous guess differs from the current guess that we're making based on this equation here. We need this because essentially our condition is going to be to check to see when this value for guess diff gets to be really small, which means that basically our estimate of the square root is not changing, which means we've found our square root. So we can also add in a counter variable here, which is just going to be 0, to tell us how many times in our while loop we have to do the calculation before we get a reasonable number. So we can say that our condition is that while our guess diff value is greater than, let's do something like that, 0.00001, we'll be looking for this difference in our estimate of the square root to be very small. As long as this condition is that our guess or our difference between the estimate for the square root and the past and the current one is, as long as that difference is bigger than this very small number, we'll keep guessing for another square root value. So we can say, for instance, here, our original guess is just the value that we came into this loop with. So we store what the old value is, basically, for our guess of the square root. And then we calculate a new one. And this is going to be the equation that's above here, so 0.5 times, in this case, xn is our current guess value. So it's guess plus number divided by guess. So that's this xn plus s over xn. We'll do that calculation, then we'll print out what our guess is. So we can see that on the screen. We can take our guess difference and calculate that. And we'll do the absolute value of our original guess. So the guess that we had at the start of this iteration through the loop minus the guess we just made. So really, we could probably call this guess estimate instead of guessed, but we'll just keep it as guess for right now. And then we'll increase our counter. And I'll just show you, if you didn't know you can do this, you can do plus equals to indicate you want to increase something by some value. So counter plus equals 1, we'll just add 1 to the variable counter. It's just shorthand notation. Rather than saying counter equals counter plus 1, you can just say counter plus equals 1. And then let's put a print statement down here. And I'll review this in just a second, so if you have any questions, we'll deal with that in just a moment. But we could say the estimated square root of, and we'll put in our number in curly braces, is, this should be our value of guess, because if we've failed this condition of guess difference being bigger than some very small number, that means we should be reaching the point that our guess is not changing. And we can say it's guess after counter iterations. So the counter thing is totally not needed here. I just want to see how many times does it take to go through this while loop in order to calculate the estimate of the square root. So we've got some obnoxiously big number here. We've got some guess of the square root, which is most probably not right. And then just some starting value for guess diff. This is only needed here to make sure that we go into the while loop the first time. So it doesn't really matter what you put here, but we want to make sure that this condition, that guess diff is bigger than some very small number, is true in order to start doing the calculation of what the approximate square root would be. Inside the loop, we then just store whatever the value was for the estimated square root in the last iteration, calculate the estimate of the square root here, print it to the screen, and then store the difference between the old estimate and the new one so that we can then, in the next iteration, check and see if the old estimate and the new one aren't changing by very much, then that basically means we've found our square root. So we run this thing. And what we see here is that the estimated square root of this number is whatever, 111,091 point a whole bunch of stuff after 7 iterations. So you can see each time through here, our initial guess of the square root was this. The second time through, this was the estimated value for the square root. Then it was here, and it starts to change by less and less and less. You can see, for instance, in the last 2, the difference between the estimated value of the square root is quite small, but only then after 7 iterations do we find the final value that we have here. That is our calculated square root. Probably it would be good to do something where we actually pick a value where we know the square root of it. So if we put in 144 here, things aren't necessarily that interesting. But if we guess that our square root of 144 is 1, we know for sure we're going to be wrong. But if I run this, again, you see here after 8 iterations that it finds the square root of 12, which is the expected value. If you put in 400, you'll see it gets a value of 20 after 9 iterations. So a little bit depends on the number that you put in here. In our case, we put in some very large value and actually found the square root in only 7 iterations. But it depends a little bit on how far off your guess is from the true value for the square root when you start doing this calculation. I don't know if we can break it if we put in a negative number or something like that. Yeah, so, okay. In principle, this is not incorrect, because if we did multiply 20 by 20, we would get 400, or minus 20 by minus 20 would give us 400. But obviously, that's not the value we're really looking for when we calculate the square root of 400. I guess it is plus or minus 20. So, and if we put in a number that's much, much bigger, it may take more iterations to find the square root value, because each time it's kind of cutting in half the original estimate. So you can see, for instance, here it was 500,000, then 250, then 125, and it slowly makes its way down to finding the value of 20 in the end. But this is a pretty typical example of using a while loop where you have a condition and you want to say, do this until this condition is met. And in this case, this kind of convergence on finding a solution is a very common way in which you would use a while loop. It's to say, keep iterating until we found the actual value we're looking for. Any questions about that basic idea for how while loops are working? As you might imagine with the Dodson equation, you're making an estimate of the closure temperature. So one way in which you can do that is that you can basically use a while loop to iterate, make an estimate of the closure temperature, see how much it differs from the last closure temperature estimate you made, and keep iterating until the difference between the estimate you just did and the previous estimate is very small, at which point you could say, okay, we found a good estimate of the closure temperature. A while loop would be a good way to do that. You can also do it with a for loop, but yeah. So there's some extra stuff in here. This is on the course page as well, that you can find a little bit about the calculating an effective closure temperature with some of the equations that we're going to use in the exercise, but we'll sort of leave it there for right now. You'll also find on the course page, and maybe in the interest of time, I'll just show you the notebook from the course page with the solutions and things already filled in there. There's this thing about logarithmic scaling and plot axes. So I'm guessing you've seen plots where you have a log axis before. So in the cases for some of the plots you'll make in the exercise for today, you're asked to use a log scaling on one of the axes of the plot. So basically just need to know how to do that. And that's what this little part of the Python concepts goes through, is basically how to do log scaling for plot axes, which is what's shown actually at the end here. It's quite simple in the sense that you just have to say set y scale log, for example, to make the y-axis have a log scale when making a plot in Matplotlib. So you can see, for instance, here, then you have a log scale along this y-axis. There's also something in here about using a function in NumPy called log space. So I'd suggest taking a look at this because essentially this is a way that when you have a log axis, to get the points to be equally spaced along the log axis in a NumPy array, you have to use the log space function to do that. It will result in nicer looking plots if you do that when you have a log axis. But I'm just going to leave that there for you to have a look at on the course page. You can refer to that when you work on the exercise. But in the remaining just minute or two that we have, I would like to just quickly show you this week's exercise. So as you might imagine, it's about diffusion and Dodson's equations. And there's two problems. First problem is basically just looking at a solution to the diffusion equation to kind of get some idea of how it works and how things like the diffusion constant affect diffusion process. So you start here just with an example of the diffusion equation, and then you're given a solution that uses this complementary error function. It's something you can find in the SciPy package, and so you don't need to worry about like calculating this. You can just use it like a normal function, but you'll be asked to calculate some kind of concentration profiles with space and time for things kind of like the example of this atoms of A and B and how the concentration changed over time. You'll do some things like that, and you're given some instructions about how to set things up initially, and you'll do then a calculation of these different diffusion profiles over time. That's more or less what you do for the first part. And there's some instructions, for instance, here about how to find this complementary error function from the SciPy package. You make some plots, you play around a little bit with different diffusivities, and that's it for part number one. For part two, you're going to play with this Dodson equation. So you have these two that we've already seen, and you're going to go through the process of estimating closure temperatures using this Dodson's method. You're given the task of making a function for doing this because we'll use this again later in the course. And so your first step is to create a function with these different parameters where you can specify things that are needed for the Dodson's equations to work. And there's some hints that are given here about how to do this. And you'll make a function called Dodson. And then there's some test cells here that are, if your equation or if your function's working properly, these test cells should work and should give you back the values that are here in this test, saying that it should be equal. When you estimate your closure temperature from Dodson, you should get a value that's equal to this one when you run the test cells. And there's, I think, four test cells to make sure your function's working properly. Then we play around a little bit with different cooling rates. So you make an array of cooling rates to look at how the cooling rate affects the closure temperature that's calculated. And then you do those calculations using your function, make some plots with that. Then you do the same thing where you change the grain size, and with a constant cooling rate, again, make some plots of that. And then finally, you look at a couple different chronometers. So different systems, so helium and apatite, helium and zircon, and then argon in muscovite. You're given the activation energies and things that you need for this calculation, but then you're just looking at the difference in closure temperature for those different systems. Do the calculation, and again, plot your results. And then there's a couple questions at the end that are optional for you to kind of think about what you've done. And that should be it for exercise number 3. Do you have any questions? Yeah. Yeah, we should at least get some general feedback. I'm not sure. I guess maybe Levi hasn't, like the course assistant Levi hasn't started grading exercise 1 yet. But once he does, I can ask that he gives at least a little bit of feedback about the how things went. And of course, if you have questions about why you didn't get full points on something or whatever, you're always welcome to ask Levi or myself, and we can kind of explain what we were looking for. But I think he was sick maybe part of last week, so he's a bit behind on some things. Anyway, I think that's plenty of material for today. And so exercise 2 deadline, we can extend that to the end of the day on Wednesday. And if you have any questions or issues with your CSC notebooks or whatever, I'll hang out here for a few minutes. Probably, I don't know if there's another class after this, but let me know if you're having issues. And otherwise, next week we'll do stuff with the advection equation. And again, Friday, the exercise help sessions are available. So see you guys next week.